Unit 2B, Lesson 4, Domain and Average Rate of Change. So we're going to look at different functions. Given a situation, determine what values, input values make the most sense or are logical for that. We'll also use different types of functions to find the average rate of change over the course of an interval. At an ice cream shop, the profit, P of C, is modeled by the function P of C equals 0.87c, where C represents the number of ice cream cones sold. An approximate domain for this function is, so of the four choices, which one makes the most sense in terms of the domain, the input value, which is C, the number of ice cream cones. First of all, if we're talking about ice cream cones, we can't have a portion of an ice cream cone being sold, so we can eliminate choices 3 and 4. Can't be a rational number. Also, now we have it narrowed down to be between 1 and 2, integers less than or equal to 0, or integers greater than or equal to 0. Well, you're not going to sell a negative number of ice cream cones. That wouldn't make you a profit, so the values have to be greater than or equal to 0. So the correct choice is going to be option 2, an integer greater than or equal to 0. In this example, the function h of t equals negative 16t squared plus 144 represents the height h of t in feet of an object from the ground at t seconds after it is dropped. A realistic domain for this function is, and then we have all those options. So our input value in this case is t, the output is h of t. So we're looking for the height of an object, or this models the height of an object, t seconds after it's been dropped. So what might help us answer this question is looking at the graph. So the vertex is going to be the ordered pair 0, 144. And then we're going to have some x-intercepts of negative 3 and 3. If we would put negative 3 in for t, negative 3 squared is 9. 9 times negative 16 is negative 144. Negative 144 plus 144 gives us 0. So that would be our x-intercepts. So the values we're restricted to right now are from negative 3 to 3 for our t values. T is our input, so it represents the x-axis, the x variable. That's the same as t right now. So negative 3 to 3, because we're looking for when an object hits the ground, which is modeled by the x-axis, any value below the x-axis is going to be below ground level, and we have to exclude those values. So right away we know our input values are from negative 3 to 3, so we can eliminate all real numbers, and we can eliminate this option because we're not even looking for h of t. We're not looking for the output, we're looking for the input, the domains. So it's either going to be choice 1 or choice 2, negative 3 to 3 or 0 to 3. T represents time. We can't go back in time, we can't have negative time. So we also have to exclude values less than 0. So we start at a t value of 0. We go until we get to a t value of 3. This represents the path of the object, the time it took for the object to hit the ground. So the best choice is going to be choice 2. 0 to 3 seconds. That is the most realistic domain for this function. Example 3. An astronaut drops a rock off the edge of a cliff on the moon. The distance d of t in meters the rock travels after t seconds can be modeled by the function d of t equals 0.8 t squared. What is the average speed in meters per second of the rock between 5 and 10 seconds after it was dropped? So what we need to do is find two ordered pairs, because then we can find the slope between those ordered pairs. Slope is referring to the average speed over this interval. So a new notation, this is called function notation. We're taking our function d of t. I need to find the value of that function when t is equal to 5. So that's what this means. I'm finding the value of the function d of t when t is equal to 5. So if I take 5 squared, that's 25. 25 times 0.8 is where this 20 gets us. So when t is 5, d of t is 20. Same thing for a t value of 10. If we would plug 10 into our equation, 10 squared is 100. 100 times 0.8 gets us 80. So when t is 10, our function value d of t is 80. So we have two ordered pairs. We have the ordered pair 5, 20, and we have the ordered pair 10, 80. If we're looking for the average speed, we're just finding the slope between these 2 points. It's the same thing we did earlier in the year. We just have a different notation applying it to this function. So we need to find the value of m, the slope. So it's 80 minus 20 divided by 10 minus 5. So we'd have 80 minus 20 is 60 divided by 5. So the average speed is going to be 12, and then our label is going to be meters per second. So for this rock, the distance it travels between 5 and 10 seconds after it was dropped. The average speed over that interval is 12 meters per second. Example 4, the graph below shows the distance in miles m hiked from a camp in each hours. So along the y-axis we have miles, along the x-axis we have hours. We want to determine which interval had the greatest rate of change, which interval has the largest slope. So we're looking at from 0 to 1, from 1 to 2, 2 to 3, 3 to 4, 4 to 5, which one has the greatest slope. And just looking at this logically, we can kind of narrow it down to which one had the greatest slope. But from 0 to 1, we're looking at rise over run. So from 0 to 1, we have to go up 2 over 1. So that would be 2 miles per hour. So we have 2 miles per hour. That would be a rate over the first interval. The second interval, we go from 1 to 2, we go from 2, we go up to 3.5 over 1. So this would be 1.5 divided by 1, or 1.5 miles per hour. From 2 to 3, we go from 3.5 to 4.5, so we have a change of 1 and a change in time of 1, so that would be 1 mile per hour. Then from 3 to 4, we go up 1/2, so from 4.5 to 5, so that would be 0.5 miles per hour. And then the last one, there is no change, that is a horizontal line, so that would be 0 miles per hour. Now looking, we have the slope, the rate of change over the course of each interval, which one had the largest rate of change, the largest slope, and that would have been the first interval from 0 to 1. That rate of change was 2 miles per hour. Rise over run, change in y over change in x. Now to the last example, the table below shows the average diameter of a pupil in a person's eye as he or she grows older. So we have the age in the left column, the average diameter in the right column. The age is going to represent our input. The average diameter of the pupil is going to represent the output. So we want to determine what is the average rate of change of the diameter of the pupil from 20 to 80 years old. So we're using the ordered pair 20, 4.7, and 80, 2.3. So to find this average rate of change, we're subtracting our y values. So 2.3 minus 4.7 divided by 80 minus 20. 2.3 minus 4.7 is negative 2.4 divided by 60, which simplifies to negative 0.04, and the label on that would be millimeters per year. So the average rate of change in the diameter of the pupil for a person going from 20 years old to 80 years old is going to be negative 0.04 millimeters per year. Average rate of change is referring to the slope between those 2 points.